In this video, we will write and optimize a few simple routines from linear algebra. Along the way, we'll see why some optimizations make code dramatically faster, while others do almost nothing. These lessons will set up a future video where I show how I progressively optimized a matrix multiplication algorithm that, when single-threaded, gets roughly competitive with established implementations while staying fully written in safe Rust. The library I wrote is called LAC. It was a personal project to see how fast but elegant my implementations could be when staying fully safe, along with some other simplifications I'll discuss later. Data flows into the CPU. The CPU does some work with it, and then emits the result. There are broadly two regimes, one where the CPU is waiting on data, and one where the CPU's own throughput is the bottleneck. What decides the regime we're in is the arithmetic intensity. How much work the CPU has to do for the amount of data that has to be moved. In this matrix multiplication benchmark, it's clear that performance is low at the start. Then, as matrices get larger, performance picks up. But after some point, it flatlines. The goal of this video is to understand fundamentally why this occurs by optimizing routines that are inherently memory bound, routines where the flow of data is the bottleneck. The data we care about is stored in RAM. This type of RAM can be understood as two NOT gates that feed into each other. Calling the two states on either end Q bar and Q, we find that both reinforce the other. If Q bar is 0, the top NOT gate emits a 1 to Q. The bottom NOT gate emits a 0 back. The state exists as long as there is power. I'll show Q bar as a blue dot and Q as an orange dot. If orange is 1, this would make blue a 0. Suppose we want to read the orange 1 value stored. This is roughly what happens. We start with the word line at the top, abbreviated WL, powered off. First, the bit lines on the left and right are pre-charged to the same voltage. Then, the word line is powered on. This turns on some transistors on either side that open access to the inner core. Because the blue dot is at 0 volts, but the orange dot is at 1 volt, a tiny voltage difference between the bit lines is made. The right bit line stays close to 1 volt. Nothing happens there. The left bit line drops a bit below 1 volt though, enough to allow a sense amplifier to observe the right bit line has the larger voltage, so a 1 can be emitted. Then, the word line is powered off, closing access to the state, which is still preserved. Now, suppose we want to write a 0 into orange, mutating the state. The left bit line is now driven high alone. Then, like before, the word line is powered on, opening access. The bit lines now overpower the coupled inverters and force the blue dot to become a 1. Naturally, the inverters themselves push the orange state into a 0. The word line is turned off, the updated state is isolated. This was simplified, but it's more or less the same. This type of RAM is called static RAM, or SRAM. It looks like this on a die. It's incredibly fast to read and write to, but takes up a lot of physical space and is more expensive to manufacture. There is an alternative, known as dynamic RAM, or DRAM. It's a capacitor that when charged holds a 1, and when discharged holds a 0. It's cheap to make, it's very small, so it can provide a lot more storage in the same area. But it's slower. Capacitors also naturally discharge, so every 64 milliseconds or so, they need to be refreshed. This costs time. SRAM, however, is very fast. But again, it's much larger and more expensive. Engineers made a way to use both. The result is known as the memory hierarchy. We have the CPU we want to get data to. Closest to the CPU, both literally and in the hierarchy, is the L1 cache. It's small, with each core holding a very small amount of data. But this data is stored very, very close to the CPU. Retrieval here is only slower to data already in the CPU's registers. A bit further out is the L2 cache, also fairly close and holds a bit more data. Then comes the L3 cache, again having more storage. After L3 is main memory. It holds much more data, but takes the longest to deliver that data to the CPU. As you've likely guessed, caches are made of SRAM. Main memory is DRAM. The caches are designed to keep useful data close to the CPU, so when the CPU does need that data, it's much faster than going out to main memory. This is the die shot of the Apple M4 chip. The 4 performance CPU cores are here in green. The L1 cache is so close, it's within the green blocks. Then there's the L2 cache, also close by. A bit further out is the SLC, the system level cache. It serves a similar role to L3, it's just shared more broadly across the system, with components like the integrated GPU. Along the left edges are the memory interfaces that connect the chip to main memory. Main memory isn't even on this die shot. You can also think of the memory hierarchy like a friendly neighborhood. Suppose you wake up in this blue house and decide you want some cereal. You check your own fridge and find there's no milk. The fridge is the L1 cache. If milk were there, making cereal would be fast and trivial. You decide to go out and ask your neighbor. For argument's sake, let the neighbor have a larger fridge. If the neighbor had milk and was willing to share some, making cereal would still not take that long. You would just have to walk back home. By some unfortunate miracle, your neighbor has no milk either. You decide to go to the street market on the corner. This market has much more storage than a fridge. But wow, the market just went out of stock. You have to drive into the city to get the milk you need for cereal. I imagine this is how the CPU feels when it has to fetch data from main memory. Thankfully, data that is likely to be used in the future follows patterns in the way a program accesses memory. For example, data that is located close to data that was just used, or data that gets accessed over and over again. This data is kept in cache. The cache hardware is like a delivery driver, knowing to bring milk to your door the second you start taking cereal out of your food closet. Now we can start. Elementary routines in linear algebra can be divided cleanly into 3 levels. The first contains routines only involving vectors, like vector addition. The second is for matrix vector operations, like matrix vector multiplication. The third is for matrix-matrix operations. It contains the holy grail of modern computing, matrix multiplication. It's hard to describe how important matrix multiplication is. Each level is also much harder to optimize than the last. Well-optimized matrix multiplication can usually become compute-bound, but only because it uses caches carefully enough to reuse loaded data for much more arithmetic. Hopefully, we'll get to this in a future video. For this video, I discuss optimizing level 1, specifically the dot product, and scaled vector addition. The memory-bound nature of level 1 gives rise to some useful lessons about some compiler behavior, and when not to waste time even optimizing at all. I will first show the dot product, where optimizations can be done. Then, I will show the scaled vector addition, where the same optimizations do not make any difference. Finding out why will tell us when certain optimizations are worth it, and what memory-bound fundamentally means. The dot product API looks like this. It's from BLAS, the basic linear algebra subprograms. Every major scientific computing library uses BLAS at its foundation. And this is how the API for the general matrix-matrix multiplication looks. A vector is an arrow. Its coordinates are how the vector is encoded. Once the array is made, it's placed somewhere in memory. But in memory, other stuff can be around it we don't want to touch. These are pointers that point to the first element of the vector. We can increment the pointer to walk through memory to see the entire vector, but we don't want to go too far. Touching memory outside the vector's valid bounds would yield undefined behavior. This is why pointers are considered unsafe. So there's also an end argument that says how long the vector is. This is how we know when to stop. These inc arguments are strides. They handle special cases when vectors aren't contiguous in memory. If inc is 2, for example, the pointer accesses every other element. The pros of the BLAS API are that it has a simple, standardized interface. Many languages can use it. It tells callers exactly what it needs, and it's the foundation for a huge amount of scientific computing. Laypack calls BLAS expecting this API and this API alone. However, it uses pointers. It's unsafe. It's also very verbose in my opinion. I do want to emphasize though, these aren't really downsides. Libraries that use BLAS, like Laypack, are so well engineered that undefined behavior is generally a non-issue. It's just my personal preference that I like Rust, which is unique because of its approach to memory safety. We are going to get rid of the unsafe. Instead of pointers, LAC will take direct slices. It's generally encouraged if different arguments are closely related. You combine them into a nice struct for readability. Ignore this lifetime apostrophe stuff. It says that when we use this struct, the internal buffer would still be valid memory. For simplicity, I'm going to set the stride to be 1. All vectors must be contiguous. I now don't have to worry about stride mess. Strided vectors may be useful for Laypack, matrix views or something, I don't really know. But I also don't know why you wouldn't just pack any non-contiguous buffers into contiguous ones beforehand for heavy routines. This would still be much faster than traversing over strided data. But I haven't gotten there yet, so I may be naive. Regardless, the stride field is useless now. And now that memory is contiguous, n just becomes the length of the buffer, so even the n field is useless. The vector just becomes the buffer. I'm still keeping it in a struct though. The name makes it clear the buffer is meant for a vector. We will need 2 types of vectors, one that is read-only, immutable, and one that is mutable. This type system lets us change the dot product syntax into this. In my opinion, this is much cleaner. It's explicit about what it wants. 2 vectors. And again, ignore this apostrophe shit. Do focus on the F32 on the right. That tells us this vector is single precision, where each number is encoded with 32 ones or zeros. For this video, I'll only show single precision routines. The F64 double precision routines for memory-bound level 1 are line by line the same, as we'll understand soon. The only thing we do have to do now, at the start of each routine, is verify the lengths of both vectors are the same. This is still much better than BLAS in my opinion, because if you pass the wrong n there, you don't get a nice error message, you get undefined behavior. The dot product takes 2 vectors. It calculates the element-wise products. And it returns their sum. A naive implementation would look something like this. First off, we are using vector refs because they don't mutate here. We first access the internal data buffers from both vectors. Then define a mutable sum starting at 0. We iterate through both vectors at the same time and add their element-wise products to the sum. And then we just return the sum. Benchmarking on my Apple M4 with 2 vectors 1024 elements long, we find roughly 5.6 million iterations in 5 seconds occur, each iteration taking 900 nanoseconds. You may think, wow, we're in the nanoseconds. This routine must already be perfectly fast. Wrong. No, I'm kidding. It actually is crazy fast for just being a for loop, but the way the for loop accumulates into the sum is also where a slowdown occurs. We can make this faster by understanding hardware inside the CPU. Inside are 32 vector registers, each able to hold 4 F32s. With a single instruction, it's possible to do work in parallel. The scalar loop is SISD, or single instruction, single data. For each pair of elements, we calculate their product and accumulate into the sum. To more fully use the CPU, we do work in parallel. We want to do SIMD, single instruction, multiple data. This is what an SIMD implementation looks like. First, we define a constant. It tells us how many pairs we want to process together. We saw that CPU registers can only hold 4 F32s though. Hence, this logical 32-lane SIMD register would have to compile down to several instructions for the physical SIMD width. Parallel work is still being done here though. Next, we add a quick return for vectors of length 0. When there's no work to do, we return immediately. We access the internal buffers of both vectors and split them into chunks of 32 elements. We may also get a leftover tail if the length is not divisible by 32. The fixed size chunks will be dealt with SIMD. The leftover tail, scalarly like before. For these animations, each vector contains 40 elements. This gives one 32 element chunk and an 8 element tail. The accumulator is where SIMD starts. It does the same job as the single sum variable before. Instead of one scalar initialized to 0 though, we create an SIMD vector with 0 in all 32 lanes. Let's focus on the SIMD chunks first. We have one chunk from X, one from Y, and an SIMD accumulator filled with zeros. This loop iterates through matching chunks of X and Y. It converts each to an SIMD vector. It multiplies the two vectors element-wise, then adds the vector into the accumulator, all with parallel SIMD operations. Once the chunks are exhausted, we use the same scalar loop as before to handle the tail. Finally, we horizontally reduce the accumulator by adding its final 32 lanes together. Adding that to the scalar tail result gives us the dot product. You may be wondering why we use lanes as 32 in the first place instead of the native lanes as 4. By working with 32 elements at a time, we go through the logical loop 8 times less, and let the compiler split each logical vector for us. Soon, when we go through reading some assembly though, we'll learn why using lanes as for would not cause that much of a slowdown for memory-bound routines. However, if lane gets too large, it can increase register pressure and actually cause a slowdown. The CPU only has a finite number of physical registers. For example, holding an SIMD vector with 1024 lanes would require 256 4-lane registers. The code would still work, but there wouldn't be enough registers to hold all of that data at once. The compiler would need to process it in smaller pieces or temporarily store some values in memory. It would slow things down. Constants like lanes are usually tuned for each architecture to find the optimal value. We find that 42 million iterations can be done in the same time, roughly 8 times faster. With n as 1024 and lanes as 32, there is no slower scalar tail path though. This means nothing. The scalar path would work on less than 31 elements. It would also have less and less of an impact as vectors get larger. This routine also takes two vectors, x and y. It scales x by a, adds that to y, then puts the result into y itself. X is an immutable vector ref. Y is now a mutable vector mut. The loop is basically this. We have alpha, or the scalar multiplier a, and f32, and x and y. We do a quick return if alpha is 0. Then, it's literally just a scalar loop over x and y. Benchmarking, again with vectors having 1024 elements, it's already super fast. Writing the SIMD analog and benchmarking that too, we find the same performance. Comparing both implementations side by side, one is a lot more readable and elegant than the other. What's going on? There are 3 things to think about when deciding if SIMD is worth it. Vector addition is a fully independent and element-wise operation. Each ith element is updated independently. Multiple I updates can then be done at the same time. Parallel work is available. The dot product in the naive version is not independent. The inner loop involved an accumulating sum. The ith update depended on the previous update. This is what's called a dependency chain. We revealed the parallel work by defining an accumulator vector. This created many separate chains, allowing multiple elements to be processed together. At the very end, We summed across the accumulator, which took the bottleneck of that accumulating dependency out of the inner hot loop. Parallel work was also available here with a bit of restructuring. This is the generated assembly for the naive vector addition loop, which is already fast. The first 4 lines load data into 8 Q registers. These Q registers are the CPU's 32 registers I showed in that slick animation earlier. Then, it uses fused multiply add instructions on these registers. Each performs AX plus Y at a time. Then, it stores the results into Y. But wait, our naive code didn't use any SIMD. Why are there already SIMD FMLA operations on 4 indices at a time? The compiler actually observed the available parallel work and automatically emitted SIMD to optimize the inner loop. The assembly for our manual SIMD version looks the same, but is more aggressive. It works on twice as many registers at a time. But the routine didn't prove to be any faster. This is because the bottleneck here is moving data, not performing the arithmetic. This is what memory bound means. The less aggressive SIMD loop the compiler auto-generated was already enough. As vectors get super large, DRAM behavior may be a bit different. By repeatedly benchmarking these vectors many times, they are definitely kept close in cache. But my point still stands. Moving data through the memory hierarchy is more limiting than performing the arithmetic itself here. But the dot product is also memory bound. Why did manual SIMD help there? The generated assembly for the naive, slower dot product loads 8 SIMD registers and does use SIMD fmul instructions to multiply elements from x and y. But before adding these products together, it extracts individual values from the vector registers and treats them as scalar values in S registers. These fadd instructions are hence scalar addition, SISD. Every addition accumulates into S0, our mutable sum, so each one depends on the previous result. No parallel work can happen. This is an actual scalar accumulation loop, not one that looks scalar but becomes fully SIMD automatically. By restructuring, we produce an inner loop that recovers those parallel FMLA operations. Then, after the inner loop, the reduction across all lanes of the accumulator is performed. The important thing is that this happens outside the hot loop. The compiler I used wasn't able to automatically make this structural change, or it chose not to preserve the exact behavior of my code. Manual SIMD was necessary. Different lanes values could also have been chosen. There may be small, minute differences in performance some may want to consider if they want to squeeze out every nanosecond. We can imagine a scale. On the right are boxes for memory cost. The memory speed limit, how quickly memory can be transferred, called the bandwidth, and the amount of memory needed to be moved for the routine. On the left are boxes for compute cost, the amount of arithmetic work, and any dependency costs from poor or impossible parallel restructuring. With vector addition, there's no dependency. The arithmetic intensity is also incredibly low, only roughly 2 floating point operations for every 12 bytes of memory moved. So the scale crashes down to the right. Manual SIMD is definitely not worth it here. The dot product also has a very low arithmetic intensity, but there's a dependency cost in the naive version. SIMD may be worth it if the compiler can't restructure that dependency away. If it does, the routine would again run into the bandwidth limit. On the other hand, for routines like matrix multiplication, arithmetic intensity scales as the matrices get larger. For large matrices, the green box crashes way down to the left. Using caches in SIMD well is very important, and this explains the flatlining in the benchmark at the beginning. Understanding these three pillars can help decide when choosing to optimize is worth it, and when code that is readable and elegant is enough. That's it for this video. If you're interested, I have written some notes that go through what we discussed here. In my library LAC, I have made memory-bound routines in level 1 and level 2 generic over T. They accept both F32s and F64s. Because these routines are memory-bound, separately tuning every implementation and its lanes constant to account for F64s being twice as large is less important here than it would be for a compute-bound routine. This is some code from my matrix vector multiply. It uses T, shown in gold, instead of F32 or F64. The generics do get a bit ugly, but they prevent a ton of code duplication. And if you look at the benchmarks for F64s, it still does fairly well for matrices as large as 2000 by 2000. I have also written some fun notes that cover how I learned to optimize matrix multiplication. They go over the difficulties and stupid things I did along the way too. If you look at the benchmark, I've been slapping everywhere in this video. LAC does perform very well here also, especially with smaller matrices, for being fully safe. But this is where I want to emphasize something very important. Benchmark plots are made to deceive. This OpenBLAS backend, while optimized for level 3, including matrix multiplication, is tuned for smaller cache sizes, which are definitely not optimal for Apple Silicon. The roughly 10 gigaflop per second difference between LAC at the bottom and BLAS at the top might not look like much, but it is. It's tremendous. Even worse, LAC is only single-threaded. If the multi-threading capabilities of every other library on this plot were allowed, LAC would be obliterated. Thank you for watching. I hope you learned a bit and found this video interesting. Level 1 routines are simple, but I think the lessons I wanted to show are very applicable to most people. The video only involved memory-bound routines, so it wasn't actually about maxing out a CPU, so I apologize for the title. But if enough people want me to make a video on matrix multiplication, I will. It would be a lot more in-depth, but I'll try to make it as visually compelling like I did here. Again, thank you for watching.